Welcome back. Today, we're going to be going over 3 examples of word problems related to permutations, combinations, and factorials. All right, so question 1 says a company has 8 employees eligible for a 3-person task force. A asks how many different 3-person task forces can be formed. Okay, so in this case, we're going to assume that there's no difference between any of the positions in the task force. We're going to assume that there's 8 employees and we're randomly going to choose 3, and that the order of those 3 doesn't really matter because it's not like there's positions or rankings there. So what I'm going to use is I'm going to use the combinations equation. So I'm going to write C, comma 8, comma 3. Or another way we could write this is 8C3 this way. Or another way we could write this is 8 choose 3 this way. Whatever way you choose to write it, any of these is correct. The reason I'm writing 8 and 3 is because there's 8 eligible employees, so we're picking from 8 people, and the number of people we're actually picking is 8. Now recall that the combinations equation, C, N, R, is equal to n factorial over n minus r factorial times r factorial. Okay, so in this case we have n is 8, so 8 factorial over 8 minus 3 factorial, which is 5 factorial, and then times 3 factorial. Okay, so recall also that 8 factorial is the same as 8 times 7 times 6 times 5 factorial. And then on the bottom we have 5 factorial times 3 factorial, which 3 factorial is just 3 times 2 times 1. Then I can cancel out my 5s. I can also say, well, 3 times 2 times 1 is just 6, so I'll cancel this out with 6. And my final answer is just 8 times 7, which is 56. And that's the nice thing about these factorial type of equations is we can just do that. We can oftentimes get rid of a lot of the numerator and denominator because a lot of things will cancel out. Also, in a lot of data management tests, you'll be allowed a calculator. So you could also just type into your calculator 8 choose 3, and that will also just give you 56 directly. So the answer for part A is that 56 different 3-person task forces can be formed. Okay, what about part B? If the task force has a leader, assistant, and reconder, how many arrangements are possible? Okay, cool. So now there's 3 distinct roles. And so now it actually does matter what order people are picked in because it matters. Let's say it's the same 3 people, but in different roles. That would still be considered a different permutation in this case. So here we're going to use permutations because now suddenly the order we choose these people does matter. Whereas before, if we were just choosing 3 people to all have the same role, the order wouldn't matter. So here it's going to be permutation 8, 3. Recall the permutation equation in general is like this. So my answer is 8 factorial over n minus r, so 5 factorial, which again, 8 factorial is 8 times 7 times 6 times 5 factorial, and then over 5 factorial, so those cancel, and I just get 8 times 7 times 6, which we know 8 times 7 is 56, and 56 times 6 is 336. And so there's 3 times as many different ways now, and that's because basically for every single one of those 56 ways that we had before, now for each of those 56 ways, there's 6 more ways essentially, right? There's 3 factorial time, or not more ways, but 3 factorial times as many ways because for each of those 56, each of those could be rearranged into 6 different orders of these people. And now we care about the order, right? And so that's why the number went up so much, right? And there we go. All right. C says, if 2 people refuse to work together, how many valid task forces can be formed without them included? Well, here's the thing. Let's say that A and B are both included, right? So let's say A and B are included, right? Let's say it's the opposite of this, which is that not that they refuse to work together, but that they say, oh, we have to work together. We have to both be on the team. So let's say A and B are included. Well, that means that's two of the employees that are included. So now we have six left if we take out two of them because we already picked them. And now there's six other people who could be selected. And so therefore there are six different combinations of people who, or six different groups essentially of three from these eight who possibly who would have the two people who refuse to work together actually working together. Therefore, other than those six groups of people, all the other all the other groups don't have those two people, right? And so, therefore, the answer would be 56 minus 50, which would, or sorry, 56 minus 6 rather, right? Because there's six ways for two people to have to work together. And so we're going to subtract the ways that they are working together to get that there's 50 ways for them to not be working together. Now, as for the 336 one, it's a little bit different because this is for combinations. So this would be like in the case that it's a three-person task force that's being formed, just like in part A. But what if it's like in part B? Well, in that case, we have to take out 36 from the 336 to get 300. And I just want to briefly discuss why that would be. Why would we take out 36 instead of just 6? Well, in the second case, now we're choosing A and B and another person, right? So there's, of course, six possible different groups that we could pick. But now at this point, there's also six different ways we could group all those people. Like, let's say, for example, it's A, B, and C working together. Well, there's six ways to order A, B, and C, right? Let's say that it's then A, B, and then the next person, like A, B, and D. So person one, two, and four, for instance, right? What if it's person one, two, and five, right? And we have to do this until we get all six people other than these two people, A and B, who refuse to work together. Because here, essentially, we're counting the ways for all of them for A and B to be working together so that we can subtract those ways from the total ways there are for when there's no restrictions. And so for permutations, that's why we ended up doing 3 factorial times as many ways, because we also have to account for all the different, different possible ways that A and B are working together. Because regardless of their roles, if they're in a group working together, then that's not going to work if they refuse to work together. All right, let's move on to part 2. A password consists of 4 letters followed by 2 digits 0 to 9 with no repetition of characters. Part A asks, how many such passwords are possible? Okay, well, let's start with the 4 letters. Letter 1, 2, 3, 4. And then we have 2 digits 1, 2. Okay, so let's start with how many letters could possibly be the very first letter in this password. Well, there's 26 letters in the alphabet, so I'm going to say it's 26. Now, keep in mind it said there's no repetition of characters, so whatever character we chose for the first one can't be picked again for the second one. So now for the second character, there's only 25 possibilities. Then for the third one, now there's only 24 because whatever one we pick for the third character can't be one of the first two. And then for the last character, or for the last letter of the 4, it would be 23. Then, after that, it's followed by 2 digits, 0 through 9. So there's 10 different digits. So how many possible digits could there be for the fifth character of the password, or the first digit? Well, it could be any of the 10. What about for the next one? Right? What about for the final character of the password? Well, that would be any of the digits 0 through 9, except for whatever we picked the first time, right? Because there's no repetition of characters. So now there's only 9 left because it could be any of the 9 or any of the 10, except for whatever was picked. And so therefore, the answer is 26 times 25 times 24 times 23 times 10 times 9. And please feel free to use a calculator to do stuff like this. Don't bother doing this on paper or something like that. This is certainly something we would use a calculator for. So the answer is 32,292,000 different passwords could be written in this way. B asks, what if repetition of digits is allowed but not letters? Well, in this case, we would still have the 26 times 25 times 24 times 23 because the repetition of letters is still not allowed, only digits. And so in that case, we would have still these first four the same, but then instead of times 10 times 9, I'd put times 10 times 10 because we could possibly have the same digit twice, right? So there's 10 possibilities for this one, and then also 10 possibilities for the second one now that we don't have to eliminate whatever was chosen for the first digit. And so then if I multiply that out, let's see what I get. 26 times 25 times 24 times 23 times 10 times 10. That's going to be 35,880, or sorry, 35,880,000. And so there's a little bit more, right? It's a few more, which makes sense because now we have less restrictions. Repetition of digits is now allowed, whereas in the first one it wasn't. And so there's going to be more possibilities. We're essentially adding on all the possibilities now that where the digits are repeated. Okay, part C asks if the password must begin with a vowel, how many are possible with no repetition? Okay, so assuming that now we're not allowed repetition for anything, once again, and the password must begin with a vowel. Well, here's the thing. How many vowels are there in the alphabet? Well, there's A, E, I, O, U, and sometimes Y. So I guess I'll include Y here because Y is sometimes a vowel, so we'll go with that. So that's 6 possibilities then, 6 vowels. And so I'm going to put 6 here. Then how many possible values could I put here? Well, for this one, it just said the password must begin with a vowel, so the other ones don't have to be vowels. However, the other letters we choose can't be repeated. So whatever we chose here, whether we chose A, E, I, O, U, or Y, we can't choose it again. So now there's only 25 possibilities for this one instead of the full 26 because we can't choose whatever we picked for the first one, for the vowel. Then there's 24 for the third one, because now we can't choose whatever we picked for the first or the second. And then there's 23 for this next one. Then we still keep the times 10 times 9, assuming that we're not allowed to repeat any of the digits anymore. So assuming we're back to no repetition of characters. So therefore, I get 6 times 25 times 24 times 23 times 10 times 9, and this is going to be 7,452,000, which is still a lot, but that's much lower than before because there's very few vowels in the alphabet, right? By saying that we couldn't have a consonant, we could only have a vowel in the first position, that really narrowed down what we were allowed to do, and so that made for less different outcomes, right? Less different permutations there. All right, let's do one more example for today. This third one says, a club is seeking a president, vice president, and secretary from 10 members. In how many ways can the officers be chosen if no one can hold more than one position? So this would be permutations because we have a group of 10 people and we're selecting 3, and order does matter because it does matter if you're the president, vice president, or secretary. It matters what position you have, of course. And so therefore, it's going to be P permutation 10 comma 3, right? There's 3 positions we're selecting and we're selecting from 10 people. So that's going to be equal to 10 factorial over 10 minus 3 factorial, which is going to be 10 factorial over 7 factorial. And a reminder that 10 factorial is just 10 times 9 times 8 times 7 factorial over 7 factorial. So those cancel, and I just get 10 times 9 times 8. Now 10 times 9 is 90. 9 times 8 must be 720. And so therefore, there are 720 different ways the officers can be chosen. The next one says, what if 2 members refuse to serve together? How many arrangements are there now? Okay, so in order to figure this out, I'm first going to figure out how many ways there are for those people to definitely be serving together, and then I'm going to subtract those from the total, right? Because remember, we're expecting it to be less, since these were just all the ways if nobody refuses to work together. Whereas now it's how many ways are there if these 2 people refuse to both be on this club that's having the president, vice president, and secretary. Okay, so how many ways are there for these people to definitely be working together? So let's just arbitrarily say that it's A and B that refuse to work together. I would like to know, okay, how many ways would A and B have to work together? Well, the thing is, let's say A and B are both included. How many different ways could we choose the third person who's working with them? Well, there's 10 members, and so if we choose A and B, then there's a third member, right? So it's A and B, and then also 8 other choices, right? 8 other choices. And also too, these A and B and the any of the 8 other people could be arranged in 3 factorial ways, right? Because once again, we have a president, vice president, secretary. So I'll be multiplying that by 3 factorial in order to account for the fact that there are indeed 3 ways for A, B, and whoever the third person is, who could be one of 8 people, who is going to be picked. So therefore, 8 times 3 factorial is 8 times 6, which is 48. So therefore, there are 48 ways for A and B to definitely be working together, because it could be A and B and any one of the other 8 people. And those 3 people we select could be rearranged in 3 factorial ways. And so that's how we got this number. So now I'm going to subtract that number of ways that they definitely are working together from the total of all the ways to get the number of ways that they are not working together. So if I do that, I get 672. And so that's my final answer for part B, is that there are 672 possible arrangements that are still possible even if these 2 members, A and B, decide that they refuse to work together. What about part C? If the positions of VP and secretary are considered equal and only president is distinct, now how many possible combinations are there? Or I guess we might still say permutations in the sense that it's saying combinations in the question, but we could still even say permutations in the sense that only these 2 positions are equal, but the president is indeed still distinct. So for this one, we need to first choose the number of people who could possibly be the president. So there's 10 people who could possibly be president. Okay, now how many ways are there to choose from the next 9 people, from the other 9, now that we've chosen the president, for the other 2 positions, which are considered equal? Well, here we're going to multiply by 9 choose 2, right? Or I should write it actually, we've been writing it like this, because these 2 people we're choosing from the 9, the order doesn't matter, right? And the reason it's 9 people and not 10 is because we already picked the president, right? The president is one of the 10 people. So then we have 10 times 9 choose 2, which 9 choose 2 is going to be 9 factorial over 7 factorial, 2 factorial, which that's going to be 9 times 8 times 7 factorial over 7 factorial, 2 factorial. Then I'll cancel these out, and we're going to end up then with 9 times 8, which is 72, divided by 2, which is 36. So that's 10 times 36, which is 360. Therefore, if the positions VP and secretary are considered equal and only president is distinct, there's now 360 combinations, or I guess sort of permutations, sort of combinations, that are possible here.